Good day, everyone. Today, sir, I am Christian Sina, a third year BSN Mathematics students at University of Southeastern Philippines. And in this video, we are going to have a discussion all about infinite series of positive terms. So without further ado, let's start. So I'm sorry for the noises. They're just very. So in this lesson, we will explore the fascinating world of infinite series, particularly focusing on a series composed of positive terms. Understanding infinite series is crucial as they appear in various mathematical contexts and applications. We will delve into key methods for determining the convergence or divergence of these series, including the comparison test, the limit comparison test, and the integral test. Each of these methods will be illustrated with concrete examples and exercises, enabling you to develop a robust understanding of how to analyze and the behavior of infinite series effectively. So here are our learning outcomes. So at the end of the lesson, students are expected to be able to first is to explain the concepts of an infinite series of positive terms and describe how the comparison test, limit comparison test, and the integral test is used to assess its convergence or divergence. Second one is to illustrate examples of infinite series of positive terms and demonstrate the use of the comparison test, limit comparison test, and integral test to determine their convergence or divergence. The last one is to apply the comparison test, limit comparison test, and integral test to solve mathematical problems involving convergence or divergence of infinite series of positive terms. But before we proceed on the methods on determining the convergence and divergence of an infinite series of positive terms, let's first get to know what is infinite series of positive terms. So, an infinite series of positive terms are those infinite series whose terms are positive, and also it has special properties. Third is special properties. In particular, the sequence of partial sums of such a series is increasing and has a lower bound of 0. And the condition for the convergence of this series is that if the sequence of a partial sums also has an upper bound, tapos because boundedness and convergence of a sequence are equivalent, then we can say that the sequence of partial sums is convergent. And then we can then use that to conclude that therefore the series is also convergent. So we have an example for that now. But before that is the theorem 8.4.1, which states that an infinite series of positive terms is convergent if and only if its sequence of partial sums has an upper bound. So here is the example. Now it is an infinite geometric series of positive terms. So firstly, no, if it is positive, the second one is increasing. Third one is lower boundary of 0 and the upper boundary. So first, as you can see, say a partial sum, there is no such thing as negative, right? 1/3 is positive, 1/9 is positive, 1/7 is positive, and so on and so forth. That means we can then check that it is positive. Now, it is on the increasing part. Say, for example, you have here Sn plus a sub 1 plus a sub 2 plus a sub 3 plus a sub n plus so on and so forth. Okay, so if it is just about the sub 1, it will be only a sub 1. If it is S sub 2, it will be a sub 1 plus a sub 2. If it is S sub 3, it will be a sub 1 plus a sub 2 as a set 3. So let's examine this example if tracing partial sum, a sequence of partial sum, 1/3 to the power of n was. Stop with that. Now then, S sub 1 will be 1/3, right? S sub 2 will be the addition of 1/3 plus 1/9. So that will give us anyway, 4/9. So S sub 3 So from that, you can already tell that 1/3 is less than 4/9, and 4/9 is also less than 13/27. So by that, we can say the more or the greater the value for n, the greater or the larger the value for the sum of that n. So by that, we can then say that this example we have here, which is this geometric series 1/3 to the power of n, a sequence of partial sum which is increasing. And since we have identified that our example is an infinite series of positive terms, then we can just already give a check for the checklist for the lower boundary of 0 because it is already one of its properties. Now, on the upper bound, an upper bound of a series is a finite number which is greater than or equal to the partial sums of the series. So this finite number S is the sum of the series or the partial sum of the series, which makes it always greater than or equal to its partial sum. So how do we find that finite number or value in this example we have here? So since our example is already determined or identified as a geometric series, so if you were to remember, a geometric series formula in finding its sum is S equals A over 1 minus R, where A there is the first term of your partial sum or the sequence, and R there is the common ratio. So if you look in our partial sum, you can see that 1/3 is our A, which is the first term, and R, which is the common term, is also 1/3. Now then, we can then proceed on substituting these values of A and R into the formula for the sum. So value of A, which is 1/3, will be substituted over here. And value of R, which is 1/3, also will be substituted here. That me. Next thing is, let's focus on the denominator. Now 1 minus 1/3 will give us a 2/3. So if you find it hard to deal with this problem here, you can just multiply the numerator to the reciprocal. Reciprocal of the denominator, which is 3/2. Well then, 3 times 1 equals 3. 3 times 2 equals 6. Simplify that one, it give us 1/2. So that is our sum. Since we have found the sum for that series, we can just then conclude the sum S equals 1/2 give us an upper bound. This means that the partial sums of the series from the S sub 1, which is the 1/3, is increasing as it or as the value of n is getting larger and larger and larger. So as you can see, from 1/3 it gets into 40/81, which is almost 1/2. But take note that it will never ever be equal to 1/2. It will just approach it, which makes this 1/2 its upper boundary. Then with that, since the sequence of partial sums is increasing and has an upper bound 1/2, it satisfies the condition of the theorem 8.4.1 that a bounded sequence is convergent. Therefore, the infinite geometric series must also be convergent, and its sum is 1/2. Let's proceed on to the next lesson, lesson 1.2, which is the comparison test. So this method plays a significant role in determining whether an infinite series converges or diverges by comparing it to a second series with known behavior. No? The comparison test is especially useful for series of positive terms as it allows us to relate a more complex series to a simpler one, helping us make precise conclusions about convergence. So we have here our theorem. No? This is the theorem 8.4.2. Let the series summation of u sub n from n equals 1 to infinity be a series of positive terms. If you have here another infinite series, v sub n is a series of positive terms known to be convergent, and u sub n is less than or equal to v sub n for all positive integers n, then the infinite series of u sub n is convergent. So here, the series v sub n represents the simpler series that we use for comparison to conclude the behavior of the more complex series. That's the first part of the theorem. No? There are two. So the second one is about the divergence. So if infinite series of w sub n is a series of positive terms known to be divergent, and u sub n is greater than or equal to w sub n for all positive integers n, then infinite series of u sub n is divergent. Infinite series w sub n is the simpler series which helps determine the behavior of the more complex series. Infinite series u sub n. So let's have here our example. We have here infinite series or the summation of u sub n from n equals 1 to infinity, which is the summation of 1 over 2 to the power of n plus 1 from n equals 1 to infinity. So what I did here is that every examples in this module is I've made it into a step-by-step process for us or for those that is watching this to be able to understand it more easily. Okay, so the first step here is to find or to identify the simpler series, which is the infinite series of v of n, v sub n from 1 to infinity. So what do we need to do for that? So what we need to do is to find or to identify the dominant terms in the numerator and the dominant term in the denominator. So since in the numerator we only have 1, so it'll just be 1 over, so in the denominator, the dominant term which is the 2 to the power of n, because plus 1 does not have that much impact anymore if n gets larger. So that'll be 2 to the power of n. So the next thing we will do is to show its inequalities. And then also we need to prove that the behavior of that simpler series, infinite series v sub n from 1 to infinity, which is the 1 over 2 to the power of n, is similar to the behavior of the complex series, which is the infinite series of 1 over 2n plus 1. So it'll be through a table. So if n is 1, your value for the complex series is 1/3, and your value for the simpler series is 1/2. When n is 5, your value for the complex series is 1 over 33. For the value for the in simpler series is 1 over 32. For the 10, your value is 1 over 125. Your value for the simpler series is 1 over 1024. Now then, as you can observe, the larger the value of n, or the value you substitute for n for the complex series and the simpler series, you'll get a result that shows that the value for the complex series is less than on the value for the simpler series. You can see it in the comparison column, which shows that the value for the complex series is really is uh, less than the value for the simpler series. And with that, we have confirmed that the second condition, which is the u sub n is less than or equal to v sub n, is there. Okay, so one way, another way for to look for that, or to see their inequalities, is through their denominator. So as you can observe, the denominator for the complex series is always greater than the denominator of the simpler series, which is enough reason for us to say that the u sub n is is less than or equal to v sub n. Now then, let's proceed to step 3. Find the sum of the simpler series. 1 over 2 to the power of n is a geometric series, right? Since it's a geometric series, so its sequence can be in this form, right? Based on exponential properties. So, ganun diba itong sequence? If you were to plug in 1, our first term will be 1/2. So then 1/2 will now be our A, right? Now, what is for our R? It is 1/2. Then we can then just do the substitution. So A will be substituted over here in this part of the formula, and R will be substituted over here in the value for R. So doing that will give us a result of this. So 1/2 over 1 minus 1/2. So you need to first deal with this denominator, no? 1 minus 1/2. 1 minus 1/2 will give us 1/2. 1/2 over 1/2 is equal to 1. That means that 1 is our sum. Now, let's go to the conclusion. So by the theorem 8.4.1, so mo yung theorem sa pinakauna no, sa infinite series of positive terms. Ang ato ang simpler series, which is ang infinite series of v sub n, is convergent. So moving on to our next part of the theorem, it states that suppose you have an infinite series of u sub n. First thing you need to do is that you need to find a simpler value. So let's have the example 3. It is the summation of u sub n from n equals 2 to infinity equals the summation of 1 over n plus square root of n from n equals 2 to infinity. So, remember always from 2 na siya. It's not from 1. So what we need to do here is to determine whether the series is convergent or divergent. So the first thing you need to do, just like what I've said, is you need to identify a simpler series. So just like what I've said, in identifying or in the process of identifying the simpler series, you need to identify the dominant terms in the numerator and also in the denominator. So if you look at the series, is 1 over n plus the square root of n. Dominant terms in numerator. So since the numerator is just 1, just put 1. Dominant terms in denominator is n. It's n. So since it is well known, or it is really generally agreed that this is a harmonic series is automatically a divergent series. So we can say that our simpler series is a divergent series. So let's say already here that it is a divergent. If your series is divergent, it is not necessary or needed anymore to find its sum, no? you won't find a sum for it. This divergent. So now you've identified your v sub n. Now then, as you can observe in my example or in the table, what I use is 1 over 2n instead of 1n. It is because the condition for the second part of the theorem is that u sub n must be greater or equal to w sub n. Since you observe, if you try plugging in values for each sequences, so let's say here, let me just move it. Say here, it is from 2 to infinity. That means 1 is not included anymore as the value to be substituted to n. So it'll be 2. Let's say let's put in the 5 and let's put it as a 10. And then 1, if 2 were the value for n, so an approximate values, a resulting approximate value niya is 0.2929. If it's 5, if 5 is the value of n, the resulting value for that will be 0.1382. And if it is 10, there is 0.0759. So it's like that. But when it comes to 1 over n, if you're to plug into the result is 0.5, right? If you're to plug in 5, the result is 0.2. If you're to plug in 1 over, if you're to plug in 10, the result is 0.1. Now, see the difference. Compare its resulting values or approximate values. So let's say there's a table. 0.5 is greater than 0.0909. 0.2 is greater than 0.13. So 0.1 is greater than 0.050759. So as you remember, this is our u sub n sequence for this. And this is the sequence for our u sub n. So if I were to use this sequence, does it satisfy this condition? No, it won't because it's resulting values. So it won't satisfy this condition no, because the resulting values for this uh, sequence, if you were to plug in from 2 to a larger value of n, it will give you a result of it'll give you a result that is greater than the value for the sequence u sub n. So that contradicts this condition. No? So we can't use the second part of the theorem if that were the case, but if you're to use 1 over 2n, so I don't need to create a table anymore because I've already created one, which is right over here. Now then, if I were to plug in 2 as n, the value for 1 over 2n will be 0.25. If I were to plug in 5 as n, the value for simpler series is 0.1. If I were to plug in 10 as n, the value for 1 over 10, 2n or the simpler series is 0.05. So if I were to compare this value here and the value of the simpler series, plug in from 2 to a larger number, so can be seen over here, making it 1 over 2n. It will give you a comparison that the value for the u sub n, the sequence of u sub n, will become larger than the value for w sub n, the sequence of w sub n. So the proof is here in the comparison of 0.292, which is the resulting value for the u sub n, as n is equals to 2, is greater than 0.25. Also on the second part, which is n is equals to 5, 0.006767 is greater than 0.03125. No, change this one. So this is a wrong one. I'll be changing this later. So the second part, the 5 is equal to n, 0 0.1382 is greater than 0.1, right? And 0.07597 is greater than 0.05, right? So that means by using this 1 over 2n, the condition where u sub n is greater than or equal to w sub n is now satisfied. So you might be asking na, yeah, the condition it got satisfied, but is the behavior still the same? So yes, it is still the same because uh, the behavior for the use of n is decreasing and approaching to zero along or also with the sequence for w sub n. So I can say that they have the same behavior. Now then, we have already gotten u sub n is greater than or equal to the sequence of w sub n. So let's put a check on it. So the same with the example one. As you can see, since the denominator for the u sub n or the sequence for u sub n is lesser than the denominator of the sequence for the w sub n, then we can say that the sequence for u sub n is greater than the sequence for w sub n. So makes it more solid now. So now then, let's go on to the conclusion part. So since let's make three that we have gotten and we have proven that our simpler series, which is the summation of 1 over 2n as n from 1 to infinity, is divergent. So we have already have the right to put a check on this checklist over here. Now, what about the second one? So we have already gotten also this condition right. There are even two proofs for that. So that's enough reason to put a check on this one. And then as the same as the sample one, these two condition over here are also the conditions that doesn't satisfy this condition. Okay, so since these two conditions over here are satisfied, that means this condition over here are also satisfied because of those satisfaction of these two, because of the satisfaction of these two, which makes the original series or the complex series also be a divergent series. So if we were to conclude that to better words now, or proper way, so by the theorem 8.4.2, which is the comparison test, because the infinite series or the summation of W sub n from n equals 1 to infinity is divergent, and U sub n is greater than or equal to W sub n, then that means that our original series, which is the complex series of the summation of 1 over n plus square root of n from n equals 1 to infinity, which is this one, also diverges. So that's all for the second part of the theorem 8.4.2. So now let's proceed into our second part now of the lesson, which is the lesson 1.2, which is about the limit comparison test. So first, di ba, is about comparison test. So now let's proceed into the limit comparison test. So limit comparison test is a method for determining the convergence or divergence of infinite series, particularly series with positive terms. The limit comparison test is particularly useful when the series you're analyzing is too complex to apply a direct comparison by dividing the complex series to a simpler one with known behavior. So then, you have here its theorem. Theorem 1.4, I mean 8.4.3, which is the limit comparison test. So it states here that letting uh, let the infinite series of u sub n from 1 to infinity and the infinite series of v sub n from 1 to infinity be two series of positive terms. As in the first part, if the limit of u sub n over v sub n as n approaches infinity is equals to a constant number, which is greater than 0, then you can say that the two series either both converge or both diverge. So, ang first condition daw is if your limit is equal to if your limit of u sub n over v sub n as n approaches to infinity is equals to a constant number which is greater than 0. That's the first condition. And the second condition, I need you to determine if infinite series of v sub n from 1 to infinity is convergent or divergent. If it is convergent, then you can say that your complex series, which is the infinite series of u sub n from 1 to infinity, is also convergent. Yan na siya na. So, if naman, if your infinite series of v sub n is divergent naman siya, that means na ang imong infinite series of u sub n from 1 to infinity is also divergent. So, on to the second part. If the limit of u sub n over v sub n as n approaches infinity is equal to 0, and if the infinite series of v sub n converges, then the infinite series of u sub n from 1 to infinity also converges. So, first condition, dapat limit of u sub n over v sub n as n approaches infinity is equal to 0. And the second condition is that the simpler series, which is the infinite series of v sub n from 1 to infinity, is convergent. Thus, with those conditions, we can conclude that the complex series or the original series, which is the infinite series of u sub n from 1 to infinity, is also convergent. So, in the third part of the theorem states that if the limit of u sub n u sub n over v sub n from n as n approaches infinity is equals to positive infinity or infinity, that is the first condition. And the second condition is that the simpler series of the complex series u sub n, simpler series v sub n as from 1 to infinity is divergent. And that is the second condition. If those two conditions are satisfied, then you can say or you can conclude that your original series or your complex series is divergent. Now let's have an examples. So let's have first example 1. Let's explore. So consider the series. The infinite series of u sub n from 1 to infinity, or you can just read it as the summation of u sub n from n equals 1 to infinity, equals the infinite series of square root of n squared plus 1. Or, basahan na to para mas klaro is, the quantity of square root of n squared plus 1 over the quantity of n cubed plus 4. So the problem, or the thing we need to do here, is we need to determine whether the series is convergent or divergent. So same thing sa comparison test, no? Sa example ito. Ako ano siyang tangan step by step na para dili kayo isod. So first step is to identify a simpler series, which is the infinite series of v sub n from 1 to infinity. So we need to identify the dominant terms in the numerator and the dominant term in the denominator. So if you look at that function or the series, the dominant term is in the numerator is square root of n, right? So I mean square root of n squared. Then this is equal to n. And if you look at the denominator, the dominant term there is the n cubed. So that means your simpler series, which is the infinite series of v sub n, will now be equal to the infinite series of n n over n cubed. No. numerator n here, denominator n cube here. So you can just, or you can simplify it and make it 1 over n squared. Okay, so that'll act as your simpler series, which is the infinite series of v sub n. So now we can now then go ahead and do step 2, which is finding the limit. So this will be so what is the first thing you need to do? So looking at the theorem, what you need to find is the value. So what is the value for u sub n? That'll be here. What about the value for v sub n? That'll be 1 over n squared. That will be put over here, right? Now then, if you're to multiply the numerator to the reciprocal of the denominator, you'll get, so I'll just read first one para formal. So then you'll get the limit of u sub n from over v sub n as n approaches infinity is equals to the limit of the quantity of square root of n squared plus 1 over the quantity of n cubed plus 4 over the quantity of 1 over n squared. That's it. Now then, the next thing is same sa kung giingon is multiply the numerator to the reciprocal of the denominator will give you this result. N squared, or the limit of n squared plus the quantity of square root of n squared plus 1 over the quantity of n cubed plus 4 as n approaches to infinity. And after that, looking at this part here inside the square root sign, pwede naman ma-factor out sa n squared. So, which give you a result, no? Kanina, which is, after factoring out n squared, you will just believe, or ang mabilin lang sa original content or sulod sa katong square root is 1 plus 1 over n squared, no? Because n squared now here is being factored out, so mo na lang yung bilin. But still, you can, it is still equivalent on it, yeah. If you were to multiply n squared or substitute n squared back to the 2 inside the parentheses. So you will get now, or you are now over here. It's the limit of n squared multiplied to n squared quantity multiplied to the square root of n squared quantity of 1 plus 1 over n squared over the quantity of n cubed plus 4. So then the next step will be, diba, as you can see here, si n squared is pwede na nimo siya ma-applyan or ma-square, right? And a square root of n squared is n. So ang may tabo ng n squared is may siyang n right over there. Now then, after nga mahimo siyang n, can just then multiply these two terms here, which is n squared and n, give you a result, give you a result of n cube. So, di na lang atong ipantarong pa, no? So, dili na ako kayo i-elaborate sa mga wala pa nato i-tarong na part because it'll take too much time. So, I hope you are considerate about it, sir. So, now then, after that, you can just then multiply both. There's naitawag ani nga method, no? Which is multiplying both the numerator and the denominator on the 1 over the variable to the power of the highest degree, no? So 1 over n to the highest degree over 1 over n to the highest degree. So since the highest degree for the numerator and denominator is n to the power of 3, or the highest degree is 3, then we will both we will divide the numerator and denominator to n to the power of 3 or n cube. So what will happen is we can now cancel out n cube and the numerator, just n cube there, but in the denominator we can cancel out directly. So we can go ahead and separate the function for the denominator, making it n cube over n cube plus 4 over n cube. So in this way, we can cancel out n cube now. So we'll be left with 4 over n cube as our denominator. So now, and the cancelled n cube will now turn into 1. And that is the process into how we get to this point. Is the limit of 1 square root of 1 plus 1 over n squared over the quantity of 1 plus 4 over n cubed. So, if I were to ask you, can we now apply the limit? Yep, can apply it because if you were to apply limit, surely makakuha na kag value. Either it may be 0, an infinite, or a constant value. So, applying the limit is you then going to substitute infinity to the variable n. So you'll get this part after doing that, which is 1, or the quantity of 1, square root of 1 plus 1 over infinity squared over 1 plus 4 over infinity squared. So what will happen for this 1 over infinity over here? So if a value or a constant value is over an infinity, or its denominator is infinity, it will always be equal to 0. Okay, so take note of that. So that means this value over here, or your term over here, will now be equal to 0, which what happened over here? The square root of 1 is 1, and 1 times 1 is 1. So you'll get 1 as your numerator. Then 1 plus 0 is 1, so 1 as your denominator. Then simplify it, you'll get a constant value of 1. So, now going back sa ato ang theorem. It was stated in the theorem na if your limit of u sub n over v sub n as n approaches infinity is a constant, is equal to a constant value, which is greater than 0, then since we still don't know the convergence or divergence of our simpler series or the infinite series of v sub n from 1 to infinity, which is the 1 over n squared, then that is the next step we will do. It is to determine whether that simpler series is convergent or divergent. And if you were to look at this simpler series we have here, it is a P series. It is a P series. And in the P series, this will be the value for P. It is a power. In the P series, if your P is greater than 1, then it is convergent. It may be as, then that series is convergent. Now, since our P is equal to 2 and 2 is greater than 1, that means this series now is convergent. So now we have satisfied the two conditions that we need to first satisfy for us to be able to conclude that our original series or our complex series is also convergent. So that's it for the first part of the theorem. Now moving on to the second part, the example number 2. Infinite series of u sub n from 1 to infinity, or you can read it as summation of u sub n from n equals 1 to infinity. It's the infinite series of sine 1 over n squared from 1 to infinity, or n from n equals 1 to infinity. And what we need to do here is to determine whether this series is convergent or divergent. So, first thing first is about identifying the simpler series or the simpler series, infinite series of v sub n from 1 to infinity. Since sine 1 over n behaves similarly to 1 over n when the value for n gets larger and larger and larger. Now, since the behavior of sine 1 over n is the same as 1 over n, so we'll replace it as 1 over n. So this is the process na in finding the simpler term. No? So 1 over n squared instead of sine 1 over n squared. So it can be simplified into 1 over n cubed. And now, since we have identified our simpler term, we can now then apply and remember that the value for our u sub n is sine 1 over n, right? Sine 1 over n squared. And then the value for our v sub n is 1 over n cubed. So they are just substituted over there. And then this numerator u sub n will be divided into this denominator v sub n. The next is numerator multiplied to the reciprocal denominators n cube over 1, give you the result of this. So this result. Now then, if you are going to see, or if you are going to look at it at closer, have a closer look, you can cancel out n cube to the numerator and then numerator and n squared in the denominator. So you'll only be left with n in the numerator. Also this term, which is sine 1 over n. So now, looking at it, we can now apply the limit. So we are going to substitute the value of where n is approaching infinity to n, and also to 1 over n, or the value of n into the sine 1 over n. So what will happen is infinity times sine 1 over n, which is infinity times 0. So because 1 over infinity will be equal to 0. So sine 0 is 0. So now, it becomes infinity times 0. So infinity is any value from any number to infinity, no? Because any number multiplied to 0 will be equal to 0. So infinity times 0 will give us 0. Okay. So now, by that, which is limit of u sub n over v sub n as n approaches infinity is equal to 0. Now then, let's move on to the second condition, which is the infinite series of v sub n, or your simpler series from 1 to infinity, is convergent. It is still a p series with a value of p as 3 is greater than 1, then we can say that this series is convergent. Right? So now we've already known that our simpler series, which is the infinite series of v sub n from 1 to infinity, is convergent. Then we have satisfied the condition for the second part of the theorem. So then, by that, we have already satisfied the two conditions. And these two conditions are the conditions you need to satisfy to satisfy for you to be able to say or for you to conclude that your original series or your complex series is also convergent. So, this will be the correct way to conclude it now. Since the limit of u sub n over v sub n as n approaches infinity is equal to 0, and the infinite series of v sub n from 1 to infinity converges, then by the theorem 8.4.3, which is the limit comparison theorem, the original series or the complex series u sub n at infinity, which is the infinite series of sine 1 over n over n squared, is also convergent or also converges. So under the third part of the theorem, let's also have another example for that one. No? So it is on the example number 3. So this time it is about logarithmic. So in this one, it will be just a little bit short now. So I'll be just moving this for first. So in this example, we have here our series or infinite series u sub n from 2 to infinity. So take note of this now, it is from 2. It is a summation of u sub n from n equals to infinity, which have the value of infinite series of L and n over n from 2 to infinity. So the problem here, what we need to do is still the same. It is determining whether the series is convergent or divergent. So step 1, still the same. Yeah. Step 1 is still about identifying the simpler series of the complex series. So this time we'll be using W sub n now since it is an example for the third part of the theorem. So actually, let me correct myself. It is actually just for the comparison test or direct comparison test where there is W sub n. So this should be V sub n. Sub n. Very sorry for that. I acknowledge my mistake there. Okay, that will be V sub n. So the first step is about identifying a simpler series, which is the infinite series of V sub n from 2 to infinity. So if you were to look at our series now, ln n over n. So if you were to look for or to identify the dominant terms and then dominant term in the denominator is that you can't use ln n again. And that is because the value for our simpler series because it will just be still the same. So instead of using this, we will be using 1. Always there will be invisible. There will be 1, right? Like for every x, variable x, there will be 1. So we'll be using the value 1. So that means that 1 is our numerator and n is our denominator. So with that, we have now identified a simpler series. So it is stated here that we compare it to the simpler series of infinite series 1 over n from 1 to infinity. Now then, we need to satisfy the first condition. So next thing we need to do is to find the limit. No? It is by applying limit. So same process because it is the first step or the first condition. The third part of theorem is finding the value for its limit, which is the infinity or positive infinity. So it is limit of u sub n over v sub n as n approaches infinity. So the value for u sub n is ln over n, right? So that is substituted over here. The value for vn is 1 over n. And that will be substituted in the as the denominator. The same process, multiply the numerator to the reciprocal denominator will give you this, which is n multiplied to ln n over n. So as you can observe, you can cancel out n from both numerator and denominator, right? And by doing that, you will just be leave ln n. So since we've come that far, so if I were to ask you, can we apply limit now? Okay, it is now possible. So if you're to apply limit, you substitute the value where n is approaching to n. So it will give you a result of ln infinity. And ln infinity is equals to infinity. So now we've satisfied our first condition, which is the limit of u sub n over v sub n as n approaches infinity is equal to infinity, which is this one, right? So now, the next condition, we need to find if the infinite series of v sub n from 0 to infinity diverges. So, if you were to remember, or if you if you were to try to identify this series, 1 over n is a harmonic series, right? And a harmonic series is always divergent. So this one is divergent. But if you are not that much familiar with harmonic series, you can still use P series now. Wherein P is equal to 1, which is equal to 1. So that means we can conclude that it is really then a divergent series, right? So since these two conditions were satisfied, wherein these two conditions were actually what we need to determine or to find for you to be able to conclude that your original series or your complex series, which is the infinite series of u sub n from 1 to infinity, is also convergent. So formal conclusion for that is since the limit u sub n over v sub n as n approaches infinity is equal to infinity, and the infinite series of v sub n from 2 to infinity diverges, then by the theorem 8.4.3, which is the limit comparison test, the original series or the complex series, infinite series of u sub n from 2 to infinity, which is the infinite series of ln n over n from 2 to infinity, also diverges or is also a divergent series. So now let's move on to our next lesson, which is about the integral test. So in this lesson, we'll be exploring integral test, a method for determining the convergence or divergence of an infinite series, particularly those involving positive terms. The integral test works by relating the behavior of a series to an improper integral if the integral of a related continuous function converges, so thus the series, and if the integral diverges, the series follow suit. This test is especially effective for series where the terms decrease monotonically. So this will be the theorem for that uh, method now, which is theorem 8.4.4, which is it is the integral test. So it states here that let f be a function that is continuous, decreasing, and positive valued for all x that is greater or equal to 1. Then the infinite series, this one, is convergent if the improper integral exists, and it is divergent if the limit of f of x dx from 1 to b as b approaches to infinity is equal to infinity. So that means that before you can use the integral test is that you must first ensure or be sure that that function that you've defined from your series is positive, continuous, and decreasing for all value of x where the series is started. So let's have a small definition of it now. So positive means that the function derived from that very particular series is positive for all value of x greater than or equal to the value where your series started. So this ensures that the area under the curve is non-negative. Talk about the of continuous part. So the continuous is the function should not have any discontinuity on the interval from 1 to infinity, right? So say for example you have here a graph. So we have here an example of an equation, problem which is 1 over the quantity of n minus 2 squared. So if n is equals to 2, then 2 minus 2 will be 0, and you'll be given a result of 1 over 0, which is a discontinuous because it is an indeterminate. So our x there is n now instead. So if the value of n is 2, then our function is discontinuous at that value. So since it is discontinuous at that value, then it does not satisfy the condition, no? Because it is 2 and that value is within or inside the 1 to infinity. So, but there's an exception for that. No? So say for example, your n, the problem will be changed into 1 over 1 over the quantity of n plus 2 squared. Then, if that were the problem, then if your n is equal to negative 2, then it'll turn into a discontinuous or an indeterminate result. But then, if that were the case, it is still uh, considered, or it is still continuous because this theorem, or the integral test just require you that the function must be continuous from 1 to infinity. And since you've identified that the function is continuous at negative 2, and that negative 2 is not within, or it's not from the range of 1 to infinity, then that means that that case is uh, considered okay. So that means that function you have there, which is 1 over n plus 2, or 1 over the quantity of n plus 2 squared, is continuous from 1 to, from all value of n greater than or equal to 1. Decreasing is ang function must decrease or remain constant as x increases. This allows for meaningful comparison between the series and the integral. So those are the brief definition for those three conditions before you can apply the integral test. So here are the steps to check the condition. I'm checking the positivity. First is, or the thing you need to do here is that you need to verify that the function is greater than 0 for all x, for all value of x that is greater than or equal to the to where the value, or to where the series started. No? Example is f, or the function 1 over x is greater than 0 for all x which is greater than or equal to 1. So 1 over x is always greater than 0 for all value of x greater than or equal to infinity, because from the interval 1 to infinity, if you're to plug in the smallest possible value you can plug in to x, it will give you a result of 1, which is greater than 0. So then, onto the second part, check and the continuity. Determine if f of x is continuous on 1 to infinity. Identify any points of discontinuity in the function if none exists if x. So I've already explained this just recently. So what should be done here? So you need to show that the function is decreasing for all value of x that is greater than or equal to the to where the series started. No? For example, you have here a function of x, or f of x equals any function. What you need to first do is to find its derivative, first derivative, just the first derivative. And also, it is a must that your first derivative is always negative from 1 to infinity. So, for example, let's make it 1 over x squared. Make it a little bit simpler. So, what will happen is if you put the x squared to the top, it will turn into x negative 2. And then it will be negative 2, x negative 1. Then that will result in negative 2 for x. So by that, you can see that the numerator, your numerator is always negative, no? So then you can say that this function is, or its derivative, the derivative of this function is always negative from 1 to infinity. So now let's proceed into the examples of integral test now. So we have here the example 1, which is the infinite series of u sub n from 2 to infinity, or the summation of u sub n from n equals 2 to infinity, which has its value, which is the summation of 1 over n square root of ln n from n equals 2 to infinity, or the infinite series of 1 over n square root of ln n from 2 to infinity. So first step is to define f of x now. So what will happen is, so let's use u sub n. Your u sub n is equals to 1 over n square root of ln n, right? Now let's use the space in the left, on the right. So your u sub n, your u sub n is equals to 1 over n square root of n ln n, right? So what is the process in defining f of x there? So the process there is just simple. You just need to make u sub n plus f of x. So what does it mean? What happens there is your f of x will be now 1 over x squared of ln x. It's just simple, right? If you were to see, to look for the difference from this to this, it's just that there the variable n will be changing to x now, because that is the common form for a function, f of x. Now then, the second step is to check if that function is positive, continuous, or decreasing. So first, let's start with checking if it is positive for all value of n, I mean for all value of x greater than or equal to 2. So since x ln x, or I mean x square root of ln x is greater than 0 for all x greater than or equal to 2. So let me prove it to you. So let's plug in 2, ln2. So ln2 is 0.693,147. Then that value, if you were to square that, it will give you still a result of positive. No? So if you were to multiply it to that, that will give you a positive number. So you can conclude na the denominator x square root of ln x is greater than 0 for all x greater than or equal to 2. So onto the second one. So it is the checking for continuity, right? It is over here. So the function f of x is equals to 1 over x square root of ln x is continuous for all x greater than or equal to, because its denominator never equals to 0. So diba, may motion discontinuous if yung denominator is 0 because it is indeterminate, right? It is because if you're to plug into s- smallest possible value for x now, so it will be positive positive value. Okay, but here's the interesting part. I actually changed this value now from n equals 1 to infinity into n equals 2 to infinity, because if you're to plug in 1, root of ln 1, ln 1 is equals to 0. No, x here should be 1. Ln 1 is equal to 0, so 1 times 0. So what will happen? So next is the decreasing part. Okay, so the first thing we did is to find its derivative, right? So there's a long process for it. But the result for that very long process will be negative ln x plus 1 over 2 square root of ln x all over x ln x, which is squared here, squared. If you're to plug in value from 2 to infinity, the result will show you that the numerator will still be negative. Okay, it will still be negative. And the denominator will always be positive, no? Sa any value ranging from 2 to infinity. By that, it satisfies the condition for a function to be a decreasing one. So we are now done with the checking part. So now we can now then apply the integral test now. So how do you apply it? It's a long process now, but let's do it step by step. Here is our f of x, right? Right. So what you need to do is to find its integral or improper integral. So it'll be the integral of fx dx from 2 to positive infinity or to infinity. Just need to substitute f of x, the value for f of x there, give you this result. Now, what is improper integral? So if you were to apply improper integral here, infinity will be turned into b, and a limit will be inserted over here, which shows that as b approaches infinity. So the next step is, since we are in the integral test and we are doing integral now. So there's a lot of techniques in the integration. So what we use here is the u substitution. No? We are letting u be equal to ln x. Then get their derivative. So what will be the derivative for x? That will be dx, and the derivative for ln x will be 1 over x dx. So then, what will be the value for dx? That will be du plus 1 over x, right? dx. So if you were to multiply both sides by x, then this part will be cancelled out, right? And by that, you will have your value for dx, which is 2dx. And this value will be substituted inside the integral for dx. Now then, if you look at it closely, if you look at it closely, 1 over x times x will result to the cancellation of both x in the numerator and denominator, right? That will leave us into just the 1 over square root of u. So I won't read every step, no, like from the limit as a whole, because it'll take some time. So I'll just mention the process or the action being taken or done in that part or step. Now then, we are now in this part now. We are just now left with 1 over u raised to the power of 1/2 du. So now then, if you were to move this value on the denominator to the numerator, 1/2 will be turned into a negative. Right? So it's now like this. Now if you were to find its integral, it'll be u 1/2 plus 1 over negative 1/2 plus 1. That's what happens, right? But give us a result of u 1/2 over 1/2. And then the numerator times the reciprocal of denominator will give us a 2u 1/2. Okay, so with that, will be to this state now. The limit of 2 square root of u from 2 to b as b approaches infinity. Now then, u now, your u now, will be changed back into its former value, which is ln x. After that is si 2 ln x is si 2 ln x, where x is substituted or where b is substituted to x, will be subtracted to the 2 ln 2 square root of ln x, where 2 is the value of x. Now then, in that part, your limit now will be applied now. Where NCB approaches to infinity, will be substituted the value of b. Give a result of 2 square root of ln infinity minus 2 square root of ln 2. So what will happen here is that 2 square root of ln infinity will become infinity, and 2 square root of ln 2 will still remain the same. So infinity minus any value will still be an infinity. So with that, we've just satisfied the one of the condition of the theorem 8.4.4, or the integral test, which states that if the value for your limit of a function defined from that very particular series is equal to infinity, then that series is divergent. So if we were to conclude it in a formal way, we make it like this. Now, since the improper integral limit of f of x dx from 2 to v as b approaches infinity is equal to infinity, then by the theorem 8.4.4, which is the integral test, unit series of 1 over n root of ln x from 2 to infinity is what? It is divergent. So until the second example, it is now about convergence. So this is our series. It is the infinite series of u sub n from 1 to infinity, or the summation of u sub n from n equals 1 to infinity. So its value is infinite series of 1 over the quantity of 2n plus 1 cubed from 1 to infinity. So what we need to do here is still the same, which is to define, or I mean to determine whether the series is convergent or divergent. So same as usual, or same as the last example. First step is to define the f of x. No? And if you will to remember, it is by letting u sub n be equal to f of x. So you'll have 1 over the quantity of 2x plus 1 cubed. Now, let's proceed in the checking part function. Now to the step 2. Check if the function is positive, continuous, and decreasing. So firstly, it is the positivity. Looking at it closely, it is always greater than 0 na. 2x plus 1 cube is always greater than 0 for all x greater than or equal to 1. So next is the continuity. So in the continuity, let's make it simpler now. So in the denominator, quantity of 2x plus 1 cube. If you were to look for a value that will make the denominator be equal to 0, it will be negative 1 half. So negative 1 half is not included in the interval from 1 to infinity. So that means this function is continuous to all for all x greater than or equal to 1. Now then, for the decreasing, we are going to find its derivative. So we have here our derivative, which is the negative 6 over 2x, or I mean negative 6 over the quantity of 2x plus 1, the power 4. So the numerator is always negative, right? Because this is over here. And the denominator is always positive for all x greater than or equal to 1. That means that the function is decreasing for all x greater than or equal to 1. You can now apply the integral test. So first, same as the last example, first thing, this is our function, which is 1 over 2x plus 1 cube, or 1 over the quantity of 2x plus 1 cube. And then find its integral from 1 to infinity. Substitute this value of f of x here, then you'll get this. Okay, then apply the improper integral. And after that, we now then do the u substitution, no? Which involves about the denominator, which is 2x plus 1. We are going to let u equals b equals 2x plus 1. Then we'll get their derivative, wherein the derivative of u is du, and the derivative of 2x plus 1 is 2 dx. And after that, you just need to substitute those values to their corresponding parts inside the integral sign, or the integral. And then, by the integral theorem, you can now just then move 1/2 outside the integral sign. So, nandito na siya. Then, you'll be left with 1 over u cubed du inside the integral sign from 1 to b. Then, after that, you just need to first, diba, limit n approaches infinity. Ano pa po? Buka din yan eh. U cube will, the denominator u cube will be placed in the position of the numerator, and we'll make it into u to the power of negative 3 du. Now then, you can apply the integral integration. So limit as n approaches infinity, 1/2, then u to the negative 3 will now be u to the negative 2, because negative 3 will be plus 1 over, also the same with the power of, with the same power sa numerator, the negative 2. Then from 1 to b. Now then, to simplify this, it will be limit n approaches infinity of 1/2 multiply to negative 1 over 2 u squared. So after that, the original value of u will be substituted back, which is the 2x plus 1. And after that is this function where x will be substituted by b minus the same function where x will be substituted by 1. Okay? So you will observe b is now here. And 1 will now be here. And there's a subtraction sign there. And these two, you cannot see it anymore. Okay? And after that, since b approaches to infinity, then infinity will be substituted to the value or to the variable b. So, ngayon mo siyang negative 1 over 4 times 2 times infinity plus 1 squared plus 1 over 4 quantity 2 times 1 plus 1 quantity of 2 quantity squared. So, now then, 1 or any value over infinity will be equal to 0. That means negative 1 over infinity will now be equal to 0, will not turn into 0. Now 0 plus 0 plus 1 over 36 will give you a result of 1 over 36. That our improper integral f of x dx from 1 to infinity exists. Then we can say na katong series na to, infinite series u sub n from 1 to infinity is convergent. Since the improper integral f of x dx from 1 to infinity exists, then by the theorem 8.4.4, which is the integral test, the series infinite series u sub n from 1 to infinity, which is the infinite series of 1 over the quantity of 2n plus 1 cube from 1 to infinity is convergent. So now then, you are now done, no? So we are now here at the assessment part. So I won't be showing you these assessments. It is your responsibility. It's not to look up this assessment in this module, answer it, and be honest, no, don't look onto the answer case below. Gi-provide sa or gi-provide na ako ang ako'y nagbuhat sa module. So that's it for this module, and I hope you've learned, and I hope you give value for what you've learned, so that it won't be hard, it won't be easy for you to just forget those learnings. Okay, so that would be all, and have a good day.